So I will ask you later.
Okay, okay.
Okay, so let's start with the first question. Uh, yeah. First question, any doubts, anything? Any doubts, anything? Guys? See, they are saying that sum and the product are 10 and 30. So what does that mean? That means, so sum of eigenvalues is equal to the trace of the matrix, right? Trace of it.
Uh, yes.
That is given to be 10, right? Then they are saying the product of eigenvalues, but that is the determinant of A, right? Since determinant is an upper triangular matrix, the determinant, since A is an upper triangular matrix, determinant will be 3AB, right? That is given to be 30. What does that mean? That means AB is 10, right? Right? AB is 10, and this means that A plus B is 7, right? We want A square plus B square.
Yeah,
So
हो गया है.
ये easy है ना?
129.
Yep.
हाँ, बहुत इजी है, ऐसे छोड़ दो.
हाँ ठीक.
और बनाया क्वेश्चन, डाउट डिस्कस कर, जल्दी ही जाएगा.
Okay, so let's go to the next
तो
one.
क्वेश्चन नंबर 2 मिनट.
हाँ.
Just wait one second. Okay, question
Number
810.
कौन सा?
Question number 3 आएगा.
3. Okay.
3.
Okay. Let's see. So they're saying that A is a 3 by 3 matrix with trace A equal to 3 and determinant A equal to 2. Okay. So 3 by 3 matrix means it has got 3 eigenvalues. Call them lambda 1, lambda 2, lambda 3. Okay. If 1 is an eigenvalue of A, that means say lambda 1 equal to 1. Then the eigenvalues of the matrix A square minus 2i is, okay. So first of all, let's see that. So if lambda 1 equal to 1 is an eigenvalue of A, then lambda 1 square minus 2 will be an eigenvalue of A square minus 2i, है ना? Right? So what will be an eigenvalue of A square minus 2i? We will have 1 square minus 2, that is negative 1. That is say call it mu 1, right? Mu 1 equal to negative 1. So negative 1 is an eigenvalue. So immediately discard option A and option C. Okay. Now what can we do? Yeah, fine. Look at the trace of A is 3. So trace of A square minus 2i, that will be equal to, see, mu 1 plus mu 2 plus mu 3, right? So where mu i's are the eigenvalues of A square minus 2i. Okay, fine. But what is mu 1? Mu 1 is nothing but lambda 1 square minus 2. What is mu 2? Lambda 2 square minus 2. What is mu 3? Lambda 3 square minus 2. Then what do we have finally? We have lambda 1 square, which is 1, right? Plus lambda 2 square plus lambda 3 square, right? You have minus 8. What does that equal? That is same as lambda 2 square plus lambda 3 square, right? Minus 7. Okay. Let's keep it here. Now observe that for the matrix A, here, trace is 3, which means lambda 1 plus lambda 2 is equal to, that means lambda 2 plus lambda 3 will be equal to 3 minus 1, which is 2. right? Similarly, they have said determinant A is 2. That means the product is 2, right? But lambda 1 is 1, so this is 2, right? From here we can say that lambda 2 square plus lambda 3 square will be nothing but uh, this thing, so it will be 2 square, right? Right, minus 2 times 2, that is okay, so this will be 0, right? So what does that mean? That implies that lambda 2 and lambda 3 both are 0. 1 minute, did I make a trace is 3? 1
I
minute. हाँ हाँ बताइए भैया.
I was getting both the real values. Okay, so when I solved, so see, I know very well if the eigenvalues of A is lambda, correct?
हाँ.
Let us suppose B is equal to A square minus 2i, any
Yeah.
other matrix.
Yeah.
So the eigenvalues of the B will be lambda square minus 2i. Am I
Yeah.
right?
Right. Right.
Or 2, whatever is it.
Yep.
So here, if I am talking about lambda, see, lambda 2 plus lambda 3 is equal to 2, correct? And lambda 2 into lambda 3 is equal to 2, correct?
Yep.
So I had replaced lambda 3 by 2 by lambda, correct? Or whatever is it. That means you will get lambda plus 2 by lambda equal to 2,
Okay.
correct?
Okay.
Now, hello,
Yeah. Yeah. Go
it will
ahead.
give you a quadratic equation that will give you lambda square minus 2 lambda plus 2 is equal to 0,
Oh,
correct?
1 minute. 1 minute.
Now,
Let me just write it down.
hello,
Lambda square plus.
not plus 2 minus 2 lambda
Okay. Lambda square minus
plus
2
2 equal
lambda
to 0,
plus 2 equal to 0. Okay. So what are the roots?
plus 2 is equal to 0. Now, no, see,
Hmm.
if the lambda, say leave there. If their lambda is lambda 2, correct?
Huh.
So here will be the lambda 2 square. What are the questions they are asking? But let me check the questions first. Okay, just 1 second. Lambda 2 square, correct?
Mm-hmm.
Minus 2, correct? You need
Mm-hmm.
lambda 2 square minus 2 will be 1, and lambda 3 square minus 2 will be the other's eigenvalue, correct? Now, so this root will be lambda 2 lambda 3, lambda square minus 2 lambda plus 2 root will be lambda 2 and lambda 3. Hello,
Yeah.
correct?
Okay. The lambda 2 will be,
The
yeah, lambda 2 and lambda 3.
lambda 3. Now, the lambda 2 will be the root, so it will satisfy,
Mm-hmm.
correct?
Mm-hmm.
So you will get lambda 2 square,
Ah.
correct? Lambda 2 square minus
Ah.
2. Now, hello,
1 minute. Let me. Okay.
minus
Yeah.
2 lambda.
Minus 2 lambda 2.
Now we need the value of lambda
Yeah.
plus 2 equal to 0.
What is the root?
Now
Yeah.
we need the value of lambda 2 square minus 2. So you can write lambda 2 square minus 4 equal to minus 2 equal to,
Okay.
no, don't find the roots. Lambda 2, see, our intention is to find the values of lambda 2 square minus 2, na? So you can write lambda 2 square minus 2 will be minus 2 plus 2. 2 lambda 2 minus 4.
Okay. Yep. 2 lambda 2 minus 4.
Correct?
Yep.
Now, similarly, you can write lambda 3 square minus 2 will be 2 lambda 3 minus 4.
Yep.
Correct? Now, we can find the values of lambda 2 and lambda 3 by the above equation. Lambda square minus 2 lambda plus 2. Replace,
Yeah.
there will get the answers. Okay, that time I thought, okay, lambda, okay, I did some calculation error.
Jishan, I want to say something.
Yeah. Go ahead.
Okay, so we know
Yeah,
that
sure,
roots
sure.
of if we have a complex root or complex eigenvalue, then they comes with pair, right?
Yep. Yeah, that is fine.
So
Yeah,
we,
yeah.
yeah,
So
then
No.
we can observe the
we can
option.
say that this is the right answer.
Yeah, that is the
But
answer.
no, no. But
Yes.
what my concern was, no, my concern was that lambda 2 plus lambda 3 is 2, right? And lambda 2 into lambda
Yes.
2 is 3, right? That means that lambda 2 plus lambda 3 whole square will be 4 minus 4, which is 0, right? This is my concern. But if lambda 2 and lambda 3 square.
Basically,
Oh,
na, that is, see,
yeah, yeah,
that is
yeah.
the,
Yeah.
no, no,
Sorry,
no.
sorry.
That is not the value of lambda 2 and lambda.
This means,
Since, hello?
see, yeah, 1 minute, 1 minute, 1 minute, 1 minute. So from here, okay, from here I can say that the trace of a square minus 2i will be minus 7. Okay, okay, minus 7 का से 1 minute guys, 1 minute, 1 minute, 1 minute. lambda square minus 2, 2 होगा क्या इसका?
-5 आना चाहिए ना?
Yep, yep. Minus?
5.
Yeah, yeah. I mean, it should be this thing, no? It's, अरे यार, मेरा actually computation mistake, man. Like, this should be 6, no? Minus 6. This is minus 5, right? This is minus 5, right? So, minus 5 is coming for which one? Trace, मतलब sum of eigenvalues -1 किस में आ रहा है? 2 plus 2, sorry, 2, this is 2, this is minus 2, 2 plus 2 minus 1 minute, guys, 1 minute, 1 minute, 1 minute. Minus 1 is an eigenvalue, trace will be trace of this matrix will be minus 5. So that means you need to have, this will be minus 2 minus. Yeah, fine, fine. I mean, see, trace of matrix should be minus 5, right? Right. That means, what does that mean? That means the sum of eigenvalues should be minus 5. But you already have minus 1, right? So the other value should be like, they should be complex conjugates, right? So that will be a plus bi and a plus a minus bi. Right? Now you can observe that this will imply that a should be equal to minus 2, right? And b should be equal to 2. Okay. That means option D. Okay. Is this fine? Actually, the mistake on my side was that I concluded lambda 2 and lambda 3 are 0, but it is not possible because they are complex. It's only possible in case of reals, right? Is this okay?
Yeah.
Yes.
So, I mean, I used few properties here, right? So, the first property I used is that the trace is the sum of eigenvalues, right? The second property I used is that the determinant is the product of eigenvalues. Another property I used is that uh, when you take, okay, so polynomials, so if p is a polynomial, right, right? If p is a polynomial and if lambda is an eigenvalue of m, right, then p lambda is an eigenvalue of pm. This is the third result I've used. What else did I use?
Yeah.
Then I used the fact that yeah, that's pretty much all I used. Then I used the fact that eigenvalues, if complex, occur in conjugate pairs. This is obvious because after all you're looking at characteristic equation, right? So the roots of any polynomial occur in conjugate pairs. Okay. So these are the results I used, right? And what did I do? I looked at the trace of this matrix. So instead of looking at each of the eigenvalues, I looked at the trace and then found out that the only option which corresponds to that, that trace is option D. That's fine.
Now next question.
Yep.
Question number 4. Answer is 6, na? Kailash?
No, 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 no. 6 का square 36.
Okay, let's see. Let's do.
No, I was getting 6 only.
No, no, no.
Let's see.
2 minutes रुक जाओ.
So we know that.
Question number. Class, this is class, what is known as? Yeah, see, 36 is answer. Yeah, I got 36.
Okay.
Yeah. Class 12. Okay.
Yeah, right.
Determinant of a to the power n minus 1. Basically, directly formula. Otherwise, you can do by using the fact a into adjoint of a is equal to determinant of a into in. On
Correct.
taking determinant both the sides.
Correct. Now,
So,
yeah. Now this. Now
class
take
12
it.
only I know. Okay.
Yeah.
So, question number 5.
Okay. 5, I think we have done before.
No, no, right now also we want.
Okay. Okay. So, how did we show that there exists such a linear transformation? We exhibited one such, right? And how did we define that linear transformation? Recall that to define a linear transformation, we simply need to define it on the basis elements, right? So let's take what we do. We know that v1 comma v2 is linearly independent. See, that's what it is written. v2 is not a scalar multiplier. What does that mean? That means they are linearly independent, right? So now so what we can do? We can extend it to a basis. Extend it to a basis. What does that mean? That means we can obtain vectors such that this set v1, v2 and so on up to vn, this is a basis. What do you mean by basis? Basis of what? Basis of Rn. Recall this automatically means that vi's are elements of Rn. Okay. So basis means it's linearly independent, number one. Number two, it should span. So span of v1 up to vn is equal to whole of Rn. This is what it means. Okay. Now what we do, we define a map as follows. T of v1 is equal to v2. Okay. T of v2 is equal to v1. Okay. And T of vi equal to 0 for every I bigger than equal to 3. Okay. This is our map. Okay. This is our map. This is our example map. This example map is the existence. Now let's verify whether 1 minute guys. Okay. Yeah. So this is yeah. Now what we need to show? We need to show two things. First of all, so firstly we need to show that.
My doubt is if you are writing correct. V1 V2 is linearly independent. That's fine. Since it is not a scalar multiple. Okay. Now we can extend it to a basis. This means
भैया आपका आवाज कट गया. We can extend it to a basis के बाद क्या बोले?
what does this means?
Okay. This means
How?
that you can obtain. So you can obtain. This means you can obtain vectors v3, v4, dot 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 vn from Rn
But
such that this is a basis, such that this set is the entire set is a basis. How this is a famous theorem called the extension theorem.
No, no. See, if you are writing the V3, V4 by the help of the V1, V2,
No,
correct?
not with the help.
So,
I mean, V3, V4, they are all they are not in the span of
linearly
V1.
independent.
Yeah, they're all because basis.
Yeah, that is basis. But you are telling that you are since V1, V2, you are going to write the V1, V1, V2, Vn is basis of Rn
Yep.
like that.
I mean, the
But
entire
how you
thing is
can
a,
get? Yeah.
okay. So that means I mean basically you're asking for the proof of the extension theorem, right?
No. I am just asking that
Oh.
is V3 is the linear combination of V1, V2?
No, never,
No,
never. That could,
never. Yeah.
yeah, never.
Okay. Oh, so you are adding some V3, V4 like that, and you are telling it is a basis of Rn.
Yep.
Okay.
Actually, this method is called extending. So any linear independent, you can extend it to a basis. What does that mean? That means you add additional vectors v3, v2, v3, v4, and so on up to vn, and make it a basis.
Okay.
Okay. So basically the proof also, yeah. So suppose W is the span of v1 comma v2, right? So the dimension of W is 2, right? And the dimension of so the dimension of W is 2, and the dimension of Rn is n. So what does that mean? Uh, that means that okay. So that means that there exists some vector, call it v3 in Rn, such that v3 is in the v3 is not in the span of v1 comma v2. This exists, right? Why does this exist? Because since span of v1 comma v2 is not equal to Rn. This is why it exists, right?
Yeah.
So now what we consider now again we can say there exists v4 in Rn such that v4 is not in the span of v1 comma v2 comma v3, right? Why? Because the span has dimension 3, right? And so on. We can go on until we get some vn. Actually, we don't need the idea of dimension here. We don't even need the idea of dimension here.
Okay.
So suppose, okay, we will do this. Okay, we will do the next step. Suppose W is strictly contained in Rn, right? Then we do this. Right? So after this step also, there are two cases, right? So case one is that span of. So what we do after this, we add v3, right? So now what we have, span of v1, v2, v3, right? If this is equal to Rn, suppose, then what we have, then we have a basis, right? Then we have v1, v2, v3. I mean, I shouldn't even take Rn. I should be taking a general vector space V. Okay. V whose dimension we do not know and we do not care about. Okay. But we know that it is a finite dimensional vector space. So what does this mean?
Okay.
This means that v1, v2, v3 is a basis of V, right? Okay. Then we are done. Case 2.
Yeah.
Case 2 is, suppose that span of v1 comma v2 comma v3 is not equal to v1, not equal to v. What does that mean? That means it is strictly contained in V, right? What does that mean? That means there exists some v4 in V such that v4 is not in the span of v1 comma v2 comma v3. What does that mean? That means this set v1 comma v2 comma v3 comma v4 is Li, right? So now we have another set, updated set. So now what you do, you check whether span of v1 up to v4 this is equal to v. If this is yes, right? If this is yes, then we are done, right? If this is no, then we again have another element, say v5, which is not in the span of v1 up to v4, right? Then what we do, then we add that also to v5. This is again linearly independent. So we go on doing, right? Go on doing until, so let me just write it down. Until, so this procedure will continue until the span of v1 comma v2 up to vn is equal to v, right? For some n. Why would this stop? This will stop because v is a finite dimensional vector space, right? So this will stop at some point. So at some point we'll have a big, we have many vectors which forms a basis. So what we have done, we have included v1 and v2 in the basis. That is what we have done. We started with two vectors which are linearly independent, kept on adding it until the span is the whole space, right? So this is done specifically for v1 v2, but you can do it for any linearly independent set v1 v2 up to say vk, right? Same argument will follow. Is this okay?
Okay.
So this is a proof of the extension theorem. So what we want to show, t3 equal to t, number one. Then we want to show that t has at least 3 distinct eigenvalues. Okay. So t3 equal to t is obvious, right? Just observe this. So this is observe the transformation. Okay. Okay. Now what about distinct eigenvalues? Right? Now if you notice, what would be okay? Can we get an idea about the matrix, about T for matrix? What will that be like? V1 is going to V2, so in the first column
0 1 0
0 1, everything else 0.
0 1
V2
0
is going to V1, that means 1 0,
Hmm.
everything else 0, right? And
0 0
everywhere
0.
else you have 0, so the entire thing is 0. Fine. So now what can we say? What can you say about eigenvalues? So if you solve for the characteristic polynomial, right? Yeah, if you solve for the characteristic polynomial, what would you get?
Plus or minus 1
Yeah.
and other are 0.
Yeah, so x equal to plus minus 1 and others are 0, right? So
Yes,
we have 3 distinct eigenvalues, right?
yes.
Cool, no? This is okay. So this transformation T works. Okay. ठीक है ना भैया?
हाँ भाई मस्त है.
Let's go ahead. Okay. Okay. Number 6. Anyone else?
Number 6. Okay. Yeah, please type it out. 6 6 1 times.
कर दूं क्या?
हाँ 6 6 6.
Okay.
6 is my doubt. 7 I did.
So fine. So this is the linear transformation. Okay. This is with respect to the standard basis. Okay. So first option says maps the subspace
Yeah.
spanned by E1 and E2 into itself. Okay. What does this mean? Okay. So option A actually says, if you write it in mathematical notation, it means T of
E1 equal to E3. अच्छा two.
Okay. This means that see, basically these are subsets, no? Span of E1 E2. ये बोल रहा है कि T ऐसा एक मैप है जो इस सेट को आप S मान लीजिए, S को S में लेके जाएगा, ठीक है? This is the claim. This is the claim of the option. Let's see whether that is true. So what we do, we take an element. We take an element in S. Let's call it V. So V is an element in S. What does that mean? That means V can be written as so let V be an element in S. That means V can be written as C1 E1 plus C2 E2, right? So what will be T of V? T of V will be equal to C1 T of E1, okay, plus C2 T of E2. Is this okay? But what is T of E1? E3, right? Can we observe this, that 0 0 1 0 1 0 1 0 0? This acting on E1 will be equal to E3, right? And this matrix acting on E2 will be what? Will be E2. Okay.
Span.
So C1 into E3, right, plus C2 into E2, right? So observe that this is not in the span of E1 comma E2, right? Because this contains E3, right? Right? Is this okay?
Does not belongs to span of E1 E2. So C1 E3 plus C2 E2 है हाँ?
हाँ.
अच्छा ये E1 E2 का लीनियर कॉम्बिनेशन नहीं है, so okay, so option number A is wrong. Yeah, 100% got it.
Next पूछा गया has distinct eigenvalues की नहीं. So how do you calculate? I mean, we can simply compute the eigenvalues. Now, what will be the eigenvalues?
A minus lambda equal to 0.
One will be an
No,
eigenvalue.
no. Yeah, and minus one will be
One
two
will be
times.
eigenvalue.
Minus 1 will
Minus
also
one
be an eigenvalue, and then
with sorry
Minus 1.
one will be two time.
okay. So this, right?
Yes.
So they do not have distinct eigenvalues. Okay. Now next option says has eigenvectors that span R3, right? What does this mean? This means, see, okay, see, there will be an eigenvector corresponding to this, right? Call it V1. There will be an eigenvector corresponding to this, call it V2. And there will be an eigenvector corresponding to this, call it V3, right? Now, see, now we know that distinct eigenvalues have linearly independent eigenvectors, right? This we know, right? So what can we say? We can say that V1 or V2 linearly independent hai, right? V2 or V3 linearly independent hai, right? But we do not know whether V1 and V3 are linearly independent, right? We do not know. What we need to check? We need to check this. So how do we check this? Compute the eigenvalues. Right? How would you compute the eigenvalues? Compute the matrix. Right? Apply 1, you will get minus 1, 0, 1, 0, 0, 0, okay. Then you have 1, 0, इसमें क्या होगा minus 1, right? Okay. So observe. So one more thing you can observe. So I do not know whether, I mean, if you can recall this, okay, recall that so there is something called, okay, so for every eigenvalue, for any eigenvalue lambda, right, of a matrix A, right, there is something called an eigenspace. What is that space? An eigenspace of lambda is the set of all eigenvectors, right, which correspond to the eigenvalue lambda. Right? But that is nothing but set of all vectors, right, which is a solution of a minus lambda I equal to 0. What does that mean? This means this is the null space of a minus lambda I. Is this okay? Is this okay?
Yeah, eigenspace. Okay.
And also notice that, so what will be the dimension of the eigenspace? Of lambda.
Nullity of, yeah.
Right, that will be the nullity of a minus lambda I. One more thing I want you to notice that, see, dimension of eigenspace means what? That means correspond. So suppose, okay, suppose lambda equals to 1, okay, right, and dimension of eigenspace of lambda equals to 1 is 2. What does this mean? This means that there are two vectors v1 and v2, right? There exists two vectors v1 and v2 such that which are eigenvalues, right? So a v1 equal to v1 and a v2 equals to v2, right? And this set v1 comma v2, right, is linearly independent. This is what it means, right? Is this okay? This is okay?
Yeah.
Yes.
Fine.
So we have a linearly independent eigenvector, right?
Right.
Rohit bhai,
So,
is that matrix
so what is the
diagonalizable?
so what is the nullity of this matrix?
It will be 2.
CV2. What does that mean? That means there exist two linearly independent eigenvectors, right? Eigenvectors corresponding to what? Corresponding to
1, 1, 1.
lambda equal to 1. Okay. So there are two of them, and there is already one eigenvector, right, which is which is obviously linearly independent from the other two, okay, eigenvector corresponding to lambda equal to what was it, minus 1, no? Yeah. So how many eigenvectors do we have? We have three linearly independent eigenvectors, right? So what does that mean? That means the three of them will span R3, right? The next option says has a non-zero null space. So what is that? See, the rank of the rank of T is 3. That means the nullity of T is 0. That means it is a zero null space of the system.
Rohit bhai, if we have a rank of T is N, then there are eigenvectors form a basis for Rn, right?
Come again?
If we have matrix representation for the T which has rank N, means full
Rank
rank,
N.
full rank, then
Okay.
there are eigenvectors form a basis for Rn, right?
Right. Basis. Oh, does do the I? Let me think, bro. Are you sure this works?
Because the matrix that V will be that T will be the onto transformations.
T will be what?
Onto transformations.
T will be onto.
Yes.
Okay, just okay. Let me just think about it. So, what are you saying? Claim is that uh, basically you're saying that if T is invertible, right?
Yes.
Then
Eigenvectors form basis for eigen.
okay, yeah. If T is invertible, then what can we say? Yeah, I mean, just onto that is fine. I mean, how? But okay, invertible when you say.
Use rank nullity theorem.
Pardon, come again.
Rank nullity theorem means
So, okay, so you're saying rank of T plus nullity of T is n. So, if rank is full rank,
yeah, but
then
how the rank of T look like?
nullity of T is 0, right? So, after that,
How the rank means range of T.
okay, so the range of, so the dimension of the image space of T, right? Or the dimension of the range space, whatever.
Yeah. Now we look at an element of
This is n.
this image
Yeah.
T. We
What,
try
what,
to look
what?
image of T.
Okay.
How it look is.
It looks like TV, right? For V in
Hmm.
Rn, right?
Yes. Yes.
Now,
So now TV is a lambda V. Of
huh?
I mean, how we can use eigenvectors. This V coming from Rn, right? So
Yeah.
the eigenvectors also from Rn.
It is also from Rn. I mean, yeah, that is okay. That is okay.
But we will collect only all those. All are the means not all are linearly independent, but um, we will have at
Come again,
least
come
three
again, come
vectors.
again.
We will have at least three vectors which are linearly independent.
But how? That, I mean, yeah, that is okay. See, we will have three vectors v1, v2, v3, right?
And yeah, our claim
And
is that these three vectors are eigenvectors.
but what are these three vectors? Okay, you're claiming
This
that
has
the
to be eigenvector. Yes.
how does that work? Like how do you
TV. Okay.
huh?
TV is lambda V
No,
for
see,
item.
TV. I mean, this is the this is the range, right? So any V can be written as T into W for some W in V. That's what. This is ontoness, right? What about, see, I mean, these are what? These are basis vectors, right? So you're saying every basis vector will be eigenvector? But how do you like, how do you go about proving it? Consider this matrix, okay? 0, 0, 1. This one, right? Is this invertible?
Yes.
Okay. What are the eigenvalues?
One and one.
Just one, right?
Yes.
So what is the eigenvectors corresponding to 1? So for that, what we do, we look at A minus I, right? That is 0, 1, 0, 0. Right? Now you solve for, look at the nullity, right? So what is this? So this has rank 1, so nullity 1, right? So you can say nullity is 1. In fact, more than that, you can actually find out the eigenvector. Let's do that. Okay.
Yes, yes,
So
yes.
let's do xy, right, equals to 0, 0,
0.
right? What does that mean? That means y is equal to 0.
Y.
That's all,
Yes.
right? So basically, what is the vector we have? We have this vector, namely
1, 0.
1, comma 0. This is an
Yes.
eigenvector.
Yes.
But this is the only eigenvector.
Yes.
This is the only eigenvector of A. But this is a singleton. How can this span R2? This cannot span. Have you observed that the claim is
Yes,
false?
yes, yes. Yes.
Okay, perfect. Okay. Uh, what next? Uh, let's proceed. No?
Rohit
Uh,
bhai, when it happened that the eigenvectors are basis for Rn?
pardon, come again?
When we have a theorem, that means when it is happened that the
Yeah, that is
eigenvectors,
true. So there is one theorem which says that if
what
they
is
are
condition
distinct,
only?
distinct eigenvalues, if all eigenvalues are distinct,
Hmm.
right, distinct eigenvalues imply that eigenvectors
Oh,
form a basis.
okay. If T is diagonalizable,
Observe that this is same as, this is equivalent to saying that the matrix A is diagonalizable.
yes. Here
They are
that matrix
equal.
is a diagonalizable.
Yeah, this is actually, yeah. I mean, diagonalizable.
I mean, it is not a if and only if, no?
It is if and it is if and only if.
If distinct eigenvalues, then
That is different. No, that is different. I mean, I'm not saying
Is
this and this are
diagonalizable,
if and only if.
but
I mean,
I'm saying that if A is diagonalizable, it may
uh,
not be a distinct
yeah,
eigenvalue.
but I am not saying that if A is
Oh,
diagonalizable,
okay,
then
okay, okay.
eigenvalues will be
Okay,
distinct. That I am not saying. No, I am only
okay.
saying these two statements are equivalent. This is
Yes, yes,
different. No,
yes.
see, P implies Q, and Q if and only if R.
Hmm.
I'm not saying I'm not saying
Okay,
that
okay,
P if and only if R. This is not what I'm saying. Okay.
okay. So here this matrix is involatory, right? Means A square is I.
Where?
This matrix given. Yes.
Oh, the
Okay.
matrix which
Which is
this
a
one?
special type of matrix.
Here, this one?
Matrix given in the question
Which
6.
question? Okay. Oh, this one. Yeah.
So this
Yeah,
is
this.
involatory matrix, which is a
Right.
diagonalizable.
Okay. Wonderful.
Yeah, yes. So we can say that it has eigenvectors that span R3
Yep. Yep.
by using
So,
Neuer
what
theorem.
is the claim? Involutory?
Involatory matrix are
But
diagonalizable.
involutory means this thing, right?
A square,
Involutory
A
means
square is A square is equal to identity.
A.
yes, sir.
No, 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 no.
This is
Identity,
in
identity. It is idempotent, no?
No,
idempotent means. Okay, can we let's sort this out.
it's like
भैया आपका आवाज तो नहीं आ रहा है सिर्फ थोड़ा सा आया एक माइक्रो
it's
पहले एक माइक्रो सेकंड के लिए आया फिर एक मिली सेकंड के लिए आया
Ishan bhai, you can chat on chat box, whatever you are saying. You just put your message here.
now let's clear this definition first I think this is what Zishan bhaiya is trying to say idempotent matlab A square equal to I, right? Is this idempotent?
No, 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 no. Idempotent means a square is equal to a.
Oh, okay.
Wait. See, Rohit,
हाँ,
what daily
कुछ नहीं सुनाई दे रहा भैया, कुछ भी सुनाई नहीं दे रहा, सब कट रहा है।
भाई टाइप करके बता दो।
भैया आप या फिर आप वॉइस नोट भी भेज दीजिए ना, वॉइस नोट भेज दीजिए, मैं सुन।
by message नहीं
क्या?
let me check
ओके, हाँ लेट मी चेक सुनाई दिया।
पे भेजा
हाँ,
तो
ओके,
बोल रहा है ना कि देखो यहाँ पे जैसे लिखा हुआ है इन्वोलेटरी मैट्रिक्स, करेक्ट।
हाँ,
इन्वोलेटरी का जो फर्स्ट टू वर्ड है वो आईएन है, आईएन मतलब आइडेंटिटी होता है, ठीक है ना।
अच्छा,
तो ए स्क्वायर इक्वल टू आइडेंटिटी इज
हाँ,
इन्वोलेटरी,
ठीक है, ठीक है,
ठीक है। और जो
हाँ,
बच गया वो आइडेंटिटी।
ओके, ओके, नाइस, नाइस, नाइस। So the claim is that involutory implies diagonalizable.
Yes.
Nice, nice.
ये कैसे बता रहे हो कि होगा ही
हाँ
होगा।
वही ना, ए स्क्वायर इज इक्वल टू आइडेंटिटी, ओके। So from that you will get x minus 1 x plus 1. So this has to be minimal polynomial which is in the linear factors.
Okay, saying that x square, yeah, x plus 1,
This
x
is
plus 1.
analytic polynomial
बात
first. This is analytic polynomials, okay?
Yeah,
Yeah, now we will say that this has to be a minimal polynomial.
okay. Uh,
yeah.
1 minute, 1 minute. I'm getting a call. हेलो, हाँ भैया, हाँ भैया, किसका?
Rajesh भाई
नहीं नहीं, अभी
और
भर
आ
रहा
रहा
हूँ, अभी भर रहा हूँ, भर रहा था, हाँ हाँ।
हाँ भाई आ रहा है।
अच्छा अच्छा अच्छा, हाँ हाँ, भर दो, हाँ।
ये जो एनालिटिक पॉलिनोमियल रहता है
ठीक
ना
है, ठीक
वो
है।
होता है डायगोनलाइजेबल।
ठीक आइगन वैल्यूज, देखो इसमें में बहुत
हम्म
दिक्कत है आइगन वैल्यूज में और मिनिमल पॉलिनोमियल में, वो इस बार क्लियर होगा।
हाँ भैया, मैं क्या करूँगा ना, मैं सोच रहा हूँ इसका एक मतलब प्रॉपर एक्सप्लेनेशन, एग्जांपल्स, थियरी सब मिला के एक वीडियो रिकॉर्ड करूँगा,
हम्म
लंबा वाला, आइगन वैल्यूज,
ओके
आइगन वेक्टर्स, इनर प्रोडक्ट, ग्राम स्मिथ ऑर्थोगोनलाइजेशन, और ये क्या है इसका,
ओके
जॉर्डन कैनोनिकल। जॉर्डन कैनोनिकल मैंने खुद भी नहीं पढ़ा है ढंग से, मैं सोच रहा हूँ इन सबको मिला के
ओके।
अच्छा एक थियरी प्लस विजुअल प्रूफ प्लस एग्जांपल्स का एक वीडियो रिकॉर्ड करूँगा।
कैसे करोगे, कब, कल?
अब कब उसका पता नहीं, आज रात को करने का सोच रहा हूँ, पता नहीं, देखता हूँ, आज रात को या कल सोच रहा हूँ। या सो बेसिकली yeah, so after this, so this is an annihilating polynomial, okay. So what can you say? You can say that the minimal polynomial divides x minus 1 times x plus 1, right? This is what,
Yes, yes.
yeah. So then, but what after that you can say?
See, the minus 1 and 1, these are the eigenvalues, right? Okay, so this eigenvalue has to be in minimal polynomials.
Yep,
So
yep.
what are the possibilities for
So
minimal
that
polynomials?
means mx is equal to
Yes, this is the only
uh,
possibilities for it.
1 minute, 1 minute, 1 minute, 1 minute, 1 minute.
For one cross one, it is not possible.
Yeah,
After,
one cross one we are not considering. That leave it.
yes.
Yeah. Uh, but what? So uh, I'm not saying that this theorem is wrong, but what I think is that this step is wrong. You know, this step. I'll tell
Okay,
you
okay,
why.
yes,
I'll tell you
yes.
why. Take A to be I. The minimal
Hmm.
polynomial is what?
Minimal polynomial is x.
X.
Hmm.
No, x minus 1, right?
Ah, x minus 1.
So this is not equal to x minus 1 into x plus 1, right? Because see, what I'm saying is that minus 1 need not be an eigenvalue. Okay? Minus 1
Oh.
need not be an eigenvalue.
Hmm.
This is okay?
Hmm. Okay, okay.
But इसको this diagonalize करना है, right? So let me do this. Uh, A को मैं ऐसे लिखता हूँ. I'll write A as okay, diagonalize करना है ना, तो let's say some D यहाँ पे, और यहाँ पे कुछ तो रखना है, some D inverse A यहाँ पे P होगा. इसे अगर मैं मल्टीप्लाई करूँगा तो P A equals to D P आएगा, right? Uh, determine this. Diagonal. One, okay, we can say that A is equal to A inverse, right? Right. Right. Then इससे क्या फायदा? Something, wait 1 minute.
हेलो.
हाँ भैया बोलिए.
वो कट गया था भाई, वो नेटवर्क
हाँ
काम नहीं
ओके.
कर रही.
ओके. नहीं, हम लोग बस ये देख रहे थे कि कैसे इसको प्रूव करना है. अच्छा, आइगन वैल्यूज, आइगन वैल्यूज 1 या -1 होगा तो ठीक है.
ये को नॉन आइडेंटिटी ले लेते हैं ना. The
कम
truth
अगेन.
is, I mean, I'm saying that A is not I
नॉट.
identity.
ओके.
Then
But then, I mean, we cannot. Okay, fine. Suppose, let's say, A is not that. Then what can we say?
minus 1 has to be eigenvalue. Okay.
But -1 has to be eigenvalue. Acha, I'm thinking about some other way. Okay, I minus A, I plus B has इसके बाद क्या करूँगा?
Problem occur with A will be a minus I then. Then also it is solved. In the all both eigenvalue will be a minus 1. That time is also we
That is
got a problematic things.
right.
Yes.
You can say that Okay, I plus A is,
So you,
pardon for the,
what zero? You have to write zero there, right? Right hand side.
uh,
Right
what
hand
is it?
side.
Oh, sorry, yeah, 0.
Hmm.
Yeah, right. Oh, yeah, that doesn't work. Let me think about something else. Okay, what if, okay, let's do this way. अगर मान लो then
Rohit, bhai,
go ahead.
one more method or way we can try that. Innovative matrix are permutation matrix.
Involutory matrices
Permutations. So can you use something?
are you sure about this?
Permutation matrix.
No, all involutory are permutation.
Hmm.
No,
I'm not
not
sure.
necessarily, right?
Yes, yes, yes.
See, I mean, look at this
Yes,
matrix.
yes, yes.
Yeah. Cos pi minus sine pi, cos pi. So this is involutory, but not permutation, right? Okay, since this is involutory, let's see what happens to this. So what is this actually? Cos pi कितना होता है? Cos pi is -1 ना? Sin pi 0 0, cos pi is this
Yeah.
is inside. So the only eigenvalue is -1. Sorry, 1. Sorry, -1. Sorry. Okay, let. I was thinking about another proof. Let me just think. Okay. Uh, D1, D2, Dn over 2. Then what can I say? We can say that plus. मतलब di should be plus minus 1 more positive. After that, what can we say? Determinant, okay. Then if we have 3 by 3 matrix minus 1 more. See, what if I do this? So since but we can
Rohit,
also
bhai, can we use AMGO
can we
instead?
use AMGM, right?
Yeah, definition of diagonalizable.
Okay,
AM is
but
equal to GM.
AM
Yes.
equal to GM, yeah. But then, yeah, but then we have to see, for first of all, we have to show that, what do we have to show? Yeah, but what will we use it on? We have to show that AM1 equals to GM1, and we have to show that AM2, AM minus 1 equal to GM minus 1. But this is not the case. This might not be the case. Okay. Wait 1 minute. Yeah, this has to be the case. Okay. Uh, so this is a, let me just, since we got one condition, I'll just note this down. So AM equal to GM for all eigenvalues. But how would you prove this? I think we'll pause this here. Okay, we'll think about this later. But are you sure about this theorem? That invalidized
Yes.
diagonal.
Yes, yes.
Okay, we'll try this. We'll pause it here right now. Okay. Let's move ahead to the next question. Uh, trace. So this is easy, no? Trace of matrix. Yeah, this is cool, no? Trace of matrix. Hello.
Yes, yes.
Okay. What about question number 8? भैया आप है ना? Oh, just the two of us. Okay. I think he might be
Ishan
having
bhai
some.
is not. Yeah, network
Yeah,
issue.
he's responded. He has sent some. Okay, let's do one thing. Let's sort of. So, like, do you have any problem in 7 or 8 or anything?
When evening,
Question number?
you are talking about evening, right?
I'm talking about the this assignment sheet.
Oh, no problem. Dishan bhai is also here.
Okay.
Dishan bhai,
Yeah, hello.
you can ask. Yeah,
Yeah,
we were asking about.
what you asking?
हाँ भैया और कुछ
Yeah,
और
yeah, yeah. Doubt in this.
No, no, enough. I'm feeling sleepy.
okay, okay,
Okay.
fine, fine. Bye bye, bye bye.
So can you? So they're closing the discussion. Am I right?
Yeah, yeah,
Okay. So this
Okay, okay.
assignment
No
has
problem.
been
Next
discussed.
tomorrow we will meet.
yes.
Okay. So tomorrow we will discuss